we have a capacitor, and inside the dielectric is a plane of charge, plane of free charge of density 4 nanocoulombs per meter squared. We are going to place 0 volts across the capacitor, so you can think of that as grounding both plates. So in other words, V at 0 minus V at 4 times 10 to the minus 3 meters is equal to 0. And we want to determine the charge density on the 2 plates. So if you think about it, those positive charges are going to attract negative charges. But since the positive plane of charge is closer to the right plate than the left plate, there will be more free charges attracted to the plate at 4 times 10 to the minus 3 meters than the plate at 0. And we're going to assume negligible fringing fields. So the electric field intensity will be constant and only in the x direction. And the electric field intensity will be larger if we're between the charge and the right plate than if we're between the charge and the left plate. So let's call the charge density on the left plate rho sub S1 and the charge density on the right plate rho sub S2. So we know rho sub S1 plus rho sub S2 will equal minus rho sub S, or minus 4 nanocoulombs per meter squared. So the electric flux density field inside the dielectric will look like this. So when you're between the charge and the right plate, it will have some constant positive value, and when you're between the left plate and the charge, it will have some constant negative value whose magnitude is smaller than the magnitude to the right of the charge. And we know that the values of the electric flux density field will be equal to the charge density on the 2 plates. So on the left-hand side it will be rho sub S1, and rho sub S1 is a negative value, and to the right it will be minus rho sub S2 because rho sub S2 is a negative value and the electric flux is pointing into that plate. So assuming a uniform dielectric of permittivity epsilon, the electric field intensity inside the capacitor can be found from the electric flux density field by dividing the electric flux density field by the permittivity. So here we have the corresponding electric field intensity inside the capacitor. So the voltage drop across the capacitor, which is 0 volts, can be obtained by integrating the electric field intensity from one side of the capacitor to the other. And this integral can be broken up into 2 parts because we have a constant electric field in this region and a different constant electric field in this region. So here is that integral broken up into those 2 parts. So in each case, the integrand is a constant times dx. So when you integrate, we get that constant times x evaluated at our limits of the integration. So carrying out those substitutions, we see that rho sub S2 is equal to 3 times rho sub S1. So going back here, we just found that rho sub S2 is equal to 3 rho sub S1. So now we have two equations and two unknowns, so we can solve for rho sub S2 and rho sub S1. So rho sub S1 is minus 1 nanocoulombs per meter squared, and rho sub S2 is minus 3 nanocoulombs per meter squared.